Okay, time to do some work. A little bit of a pun there. So we're going to be looking at a concept in physics called work. Now, a slightly different definition to what we use it, for in everyday circumstances. In physics, work is when a force is applied through a distance. So obviously, some object is being pushed or pulled. A force is being applied, and it moves a certain distance. So when we talk about things like homework and things like that, well, it's technically probably doesn't actually involve a lot of work because it doesn't really involve, any forces or nothing's really moving a particularly large distance. So if it's not really work, maybe we should give you a bit more of it. Anyway, let's have a look. So we're going to get straight into it, look at the formula. Now I've got my triangle here. Now, in an exam, it's more likely it'll be given to you in this format. So work equals, and it's a capital W, force times distance. So it'll probably be given to you at the top of the page, along with all the other formulas in this format here. So we need to be able to rearrange this, but firstly let's just talk about what we've got here. So we've got a force applied to an object, and it's going to move a certain distance. Now the work here that's done is actually a measure of energy. It's how much energy it's how much energy it will take to push this object with a certain force for a certain distance. So the unit for work is actually joules. So you can almost think of it like a type of energy. Now technically calling it a type of energy isn't quite right, because if we've got something moving, we'd technically say that's kinetic energy. But work is measured in joules. It is a value of or a quantity of energy that's required to push an object through a certain distance. Now the unit for work is joules, capital J. The unit for force, remember, is our newtons. So it's how hard we're pushing or pulling it. And our unit for distance, our standard unit, is meters. So work is a measure of the energy required to push something or pull an object through a certain distance. So let's have a look at rearranging the equation now. So if I want force, alright, we'll take the force is equal to the work done divided by distance. And if we wanted distance, so if we wanted the distance down the bottom right here, that something's going to move, we could work out the distance that the object moves by taking the work done divided by the force. Okay, so one thing, I think the key take-home message here, or the key thing to just remember, is that work is a measured in joules. So it is essentially a quantity of energy. And that's important because it ties in with our whole energy is always conserved. It's never created or destroyed. Okay, so we're going to have a look, move on to an example. So we're going to look at a question, a problem. Oh, sorry, jumping forward a bit there. Sorry, here we go. Alright, so a woman pushes a child in a buggy up a ramp as shown below. The woman pushes the buggy up the ramp with a force of 100 newtons. We've also got a couple of distances here. We've got 6 meters. So the length of the ramp here is 6 meters, and the height of the ramp here is 1 meter. I'm not sure if you can see that. So it's told us she's pushing with 100 newtons. Okay, she's pushing with 100 newtons, and she's pushing it up a 6 meter long ramp that's 1 meter tall at the end there. So let's calculate the work done to push the buggy and the child up the ramp. So we take our formula. So it was work equals force times distance. So in this case it is 100 newtons times 6 meters. Now how did I know to take the 6 meters? Well, whenever we calculate the work, the force and the distance need to be in the same direction. So we've got the distance here, the 6 meters, is the direction in which she's pushing. And so that's why these two match up. So the force and the distance must be essentially line up or be in the same direction. The force is applied through this distance. So here she's pushing through the 6 meters up the ramp. She's not actually pushing the pram straight up. So in this case, that means the work is 600. Sorry, I was doing a 1 there. Alright, so in this case, our answer is going to be, let's fix that up, our answer is going to be 600, and they've been kind enough to give us the unit anyway, so 600 joules. Okay, let's look at part 2, B. The energy gained by the buggy and child. So they've told us the buggy and child altogether weighs 55 kgs, so we've got another value there. Alright, sorry, I was trying to rub that out. At the top of the ramp does not equal the work done. Okay, so the amount of energy gained by the buggy, and we've got the masses given to us here, does not equal the work that is done. Explain why these two values are not equal. In your answer, you should name the type of energy the buggy has when it reaches the top of the ramp, calculate the difference between the work done and the energy at the top of the ramp, and explain where the missing energy has gone and why this occurs. So again, it's got to do with that conservation of energy, that whole idea. So we've already calculated that we need 600 joules to get the buggy, push the buggy up along the ramp. And we can work out the amount of energy. So how much energy would it have at the top? Well, what type of energy? So that's the first part here. What type of energy does it have when it reaches the top of the ramp? Well, the answer is it's going to have gravitational potential energy. Now you need to write that in full. They don't like you to do GPE, but me writing with a mouse here, or I've got a little pen, but it's very slow. So I'm just going to put the initials there. So it's gravitational potential energy that she's gained. At the top of the ramp, she's higher off the ground, so she's gained gravitational potential energy. Calculate the difference between the work done, okay, and the energy at the top of the ramp. Well, in theory, they should actually be the same. So in theory, the energy we have at the top should equal, alright, the energy that's spent, the work done, to get up there. Now the reason it doesn't, and that's this last bit, where's the missing energy gone, is because essentially we're going to get into it, it's friction and things on the ramp, a little bit of energy gets used there. But let's have a look at this. So we've actually already worked out, the work done is up here, so the work done, the energy we need to put in to get the buggy to the top of the ramp is 600 joules, and the gravitational potential energy that it gains, that it's going to have at the top here, is actually going to be, alright, so let's work this out, so the potential energy is, if we remember, it's mass, it's one of our formulas, times gravity times height. So in this case it's going to be 55 times 10 times a height of 1. So in this case it's 550 joules. You notice both of these values are in joules. This is the energy it took to push the pram up to the top, and this is how much energy it will have, gravitational potential energy it will have up the top. So to calculate the difference, well, we take, it's just 600 minus 550 equals 50 joules. So where has this 50 joules of energy actually gone? Well, we've had to put in a little bit more energy to push it up than we end up with in terms of gravitational potential at the top because of friction. There's a little bit of friction on the wheels, or maybe even a bit of air resistance. I mean, that's unlikely, they're not moving that fast, but a bit of friction on the wheels and things, which turns some of the energy, the work that's being done, into heat energy. So friction, the sliding or the rubbing of the wheels, some of those surfaces there, that rubbing of one surface over the other, the friction, creates a small amount of heat energy. So the work that's done, our 600 joules, most of it is turned into the gravitational potential energy that we've gained at the top here, but a small amount, the 50 joules here, has actually probably been given off as heat energy due to the friction on the ramp. So C here, explain in terms of force and energy why it is easier to push the buggy and child up a ramp than it is to lift it straight up. So I'm just going to clear this, let's clear this. Okay, so I'll just slide this up a little bit. Or let's just slide it over a little bit, give myself some space. So explain in terms of force and energy why it is easier to push the buggy and child up the ramp than it is to lift it straight up. Well, if we look at the work done, so that's the amount of energy it takes to push it straight up. To push it to the top here. Well, the work done if we go up the ramp, if we roll it up the ramp, is the force times distance. And we already worked that out. That was the first bit over here that we did. So that was 100 newtons times 6 meters, and we got 600 joules. Now, to push it straight up here shouldn't really take much more energy, but let's look at that. The work done to push it to go straight up, so the work to push it straight up, all right, along here, would be the force times the distance. And in this case, to push it straight up, the force is, well, we'll need to work that one out, but the distance is just 1 meter. So what is the force required to push it or lift it 1 meter into the air? Well, the force to lift something, we're going to have to pull it up, we're going to have to match or equal its weight force in order to pull it up. So remember the weight force, alright, or our force due to gravity, is simply the mass times gravity. So that was, we said it's 55 kg times 10. So it's going to be 550 newtons is the force we're going to need it to lift. That's the weight force, so it's also going to be the force we're going to need to lift the pram straight up. So my force here is 550. Alright, so if we look at this, if we think about that just really quickly, the work that it takes is going to be 550 joules. So this equals 550 joules. And you might think, well, our answer actually gives us, we've got sort of the wrong, you might think we've got the wrong answer, because it says here, why is it easier to push the buggy up the ramp than it is to lift it straight up? Well, we already know why this value is bigger. It's because of a little bit of friction. But why is it going to be easier to do this option here? Just change my color pen. Why is it going to be easier to do this option here, which was rolling it up the ramp, than it is to do this option down here, which was lifting it straight up? Well, although they both require a similar amount of energy, or lifting it up actually even requires a little bit of less energy, look at the force. To push it up the ramp, I only need 100 newtons of force. And although, the trade-off is I'm going to have to push it for a whole 6 meters. To lift it straight up, I need 550 newtons of force. So the answer they're looking for here is that although the amount of energy needed is quite similar, or even slightly less here, you need so much more force, you need to push so much harder to push it straight up, or lift it straight up, than if you push it up the ramp. And this is a key idea. With any kind of simple machine, the energy it takes to push something, say up a ramp or lift it here, the energy is usually about the same. You might have a bit of friction in there, but it's usually about the same. But what we do is we can trade off the force we have to push with the distance it has to be pushed through. So here we need a much smaller force, but the trade-off is we have to push it a bit further. Down here, if we tried to lift it, we need a much bigger force, but we only actually have to push it for 1 meter. So this one here, going up the ramp, is definitely the easier option. If you think of a mother with a child, pushing with 100 newtons is going to be a lot easier, even if she has to do it a bit longer or a bit further, than if she has to try and push it with 550 newtons. So hopefully that makes some sense to you. All right. If it doesn't, flick back and have another look through the video, and hopefully you can figure it out. So guys, just before we finish, just to sum up, work is the amount of energy that's needed or used to push a certain object with a particular force through a particular distance. So in this case, we've calculated the energy you would need to push the pram from here, all right, with 100 newtons all the way up to the top here. And we've also looked at the work, the energy that would be needed to lift, all right, the pram 1 meter, which means pushing it with a force of 550 newtons, because that's going to be its weight force. It's 55 kg, so it's going to weigh 550 newtons. Cool, I hope you found that helpful, and we've got, I think, 1 video to go on power.